Hello guys, today I want to talk about the Q-learning based adaptive traffic signal control. I use lane area detectors, and for environment I use SUMO, which is open source. And to build the Q-learning based signal I use TraCI code in Python. So firstly, this is the screenshot of my SUMO CFG file where there is a actually three-leg intersection and detectors are located approximately 150 meters away from the three-leg intersection, and one set of detectors is located in the 60 meters approximately away upstream, and all the detectors are lane area detectors and their length is 50 meter, which represents like CCTV as we know. And I'm showing the traffic flow direction here and marked red for the reinforced learning adaptive signal where it is located. Next is the verification that I use TraCI, and I use the Q-learning, that is reinforced learning. And here I am showing the Python console for step 312 and step 2184 step. And this shows that the detectors are collected information and they go through the state, exploiting it, go to action, then predict about the next state, create the reward and Q value. Lastly, calculate the max Q state for each of the two steps. But there are several steps. I just more than 5 to 10,000 steps. I just presented here only two steps here to verify my TraCI output that I use the RL reinforced learning. Later, I will show you the simulation run also and also provide the GitHub code. And here is the pseudocode. If we look at the pseudocode and the explanation for the pseudocode, I divided into 15 steps. Firstly, initialize the SUMO, and along with that, initialize traffic light, faces, detectors, reinforcement learning parameters, and Q table for the Q learning, that is reinforced learning. Then start the simulation for each episode and step starting, then make up to it will run up to maximum steps. For within the each steps, it will observe detector counts, grouping the detectors into three groups A, B, C, and discretize the counts state. If state is not Q, then initialize the Q state. Then it will choose the action using explore, which is epsilon greedy approach. Then apply green phase. After that, apply yellow phase, advance the simulation time, and observe next of state and compute the reward. And here is the reward is the Q length. Then update the Q based on the state and action. I use the most common Bellman equation, which is used for almost all reinforcement learning. Then state to next state we get, then step to next step, and next step will be adding with phase duration, and lastly simulation is ended. This is the pseudocode, and if we look at the explanation, there are five divided part. First the initialization, then the state representation. For initialization, if we look at here, we can see that I initialize the SUMO, then traffic light phase detectors, Q learning parameters. Within Q learning parameters, we have learning rate, discount factors, and exploration rate, and create the empty Q table first. Then state representation, my state is represented by three set of detector A, B, C, and number of vehicle are grouped into three category, that is low, medium, and high, and it forming into separate discrete state, that is 1, 2, and 0. Action selection, I use epsilon greedy, and this action agent will choose the signal phase, sometimes randomly, which is exploration, and mostly it will based on the Q value, which is exploitation. So exploration and exploitation both method are used. For environment iteration, I use green phase followed by yellow phase and simulation advances for new traffic condition observed then. And in the fifth stage, if you look at that queue is updated, the queue is updated and it receives the award value, which is the queue length. Which queue length is less is better. And it updates the queue table using Bellman equation and provide the future decision over the time. This is my reinforcement learning flowchart. If we look at that, as I mentioned, that firstly traffic environment SUMO, that is, and the lane area detector ABC are grouped together. Then observe the state using count vehicle from ABC group and discretize into 1, 2 or 0 state. Then choose action. For this, I use epsilon greedy policy, that is either explore or exploit. And best queue value is selected, then apply to the signal. And within that, there is a reward. Calculate the queue length. Minus of queue length is the reward. Then apply to it to main green or side green, main road or the side road. And for each green will be followed by a yellow phase. Then update the queue table, that is state and action. And this will be calculated by the Bellman equation as I mentioned, where reward plus gamma, that is discount rate, into maximum of Q value, that is next state, will be calculated. And all these things will be go through the new state updated Q table and improve the policy. And within that queue table, the state will be 110 or like that. It will take a new state in the updated queue table. And this is all about my reinforcement learning adaptive signal control. And I use lane area detectors here. And this is the simulation and the GitHub code link I provided. And if we look at the video here, I am showing the recorded video that I run in the SUMO CFG file. We can see that the traffic is moving. This is the state. This is the initial state of the simulation. So after over the time, it will actually based on the reward, it will actually make more efficient and more adaptive as per the reinforcement learning. Here we can see that the runner.py Python file which I used, and we can see below in the console that our reinforcement learning code is running. And again, this is the Sumo CFG file. We can see that the traffic is moving from east to west bound through the main road, and from the side road the traffic are accumulating, and there are three sets of detectors here, and we can see that the traffic are moving over here. This is the uh, recorded video of my simulation, and we can see the whole process over here, and the code is running. The TraCI code I am showing here also. You can also check the TraCI code in my GitHub. And here is some question and answer. Firstly, about the state. What is the state in this queue learning? Here we use a tuple, Python tuple, and in the tuple it represents by traffic conditions by three groups of detectors, that is A, B, C, and each detectors will detect the state, and the state are small a, b, c, corresponding state are 0, 1 or 2. If 0, then no vehicle. If it is low number of traffic, say 1 to 5 vehicle, then state is 1. If the traffic is high, that is greater than 5, then it will state to 2. So we discretize the level. And here is the Python code. We can see that the Python code over here, and the state is 0, 1 or 2. 0 stands for no vehicle, 1 stands for low traffic, 2 stands for high traffic, and state is the traffic density, that is low, medium or high as I described. And we have three groups of detectors that I mentioned. This is the state. And environment, if we look at the environment, what is the environment over here? Here SUMO traffic simulation controlled by TraCI is the environment. Our environment covers road network, vehicle, its movement, traffic signals, lane area detector, E2, all are the our detector, all are the environment, and it and interacts with the we interact with the environment through the Python code. And environment has the state, which is detector data, give the reward and evolves over time, that is simulation runtime. And our environment is dynamically adjusted, dynamically done in the SUMO and reacting with the signal timing. Now let's look at the reward. What is the reward here? So reward here is the negative total queue length across all detectors is the reward. And we can see the Python code corresponding. The much the queue length, the smaller the reward. So we are actually penalty. We are assigning penalty actually, and a number of stopped vehicle or queue are detecting it, and the sum of all detectors total queue in the network is calculated, and it multiplied by -1. So our weight factor is -1, and negative because we want to maximize it, because minimizing queue length will maximizing the reward. So total queue is 15. Say total queue length is 15 vehicles, so reward is -15. If total queue length is 5 vehicles, then reward is -5. Reward is the penalty for congestion. Lower the queue, higher the reward. Here is the action. What is the action here? The action of this queue learning setup is traffic signal phase activate. So we have two phase, that is 0 and 2. 0 is for main green, 2 is for side green, and action is so 0 or 2. So we apply underscore phase action. When we whichever phase we want, we will go through 0 or 2, and action is the directly gets the green light or green time at the intersection. Then comes the agent. And is there any agent here? Obviously, we have agent. Our reinforcement learning based controller, Python logic making decision is the agent. Here only one agent we have. And this agent will choose the action, update the queue value, and run over the loop, and it controls the traffic signal. We can see that and conceptually we have agent. Our queue learning algorithm is the agent. Environment is SUMO, and agent's goal is to minimize queue, that is maximize the reward. Next comes about how many agents here. We have only one agent, that is one traffic light controller. We can see that and one queue table corresponding, and one decision making function here. A single RL agent is controlling one intersection. And if we look at here, this is a single agent reinforcement learning problem, not multi-agent problem. And here comes the Bellman equation for queue learning setup. We can see that the Bellman equation, that is queue of state and action corresponding to queue and state plus alpha, that is our learning rate, into R is the reward, negative Q value, plus gamma. Gamma is the discount factor. So alpha is the learning rate, gamma is the discount factor, Q of S prime A prime, which corresponding to next state, minus Q of SA, that is current state. So our next state will multiply with state will multiply with next state and current state. So our current state will be connected with next state. Next state will be connected with the current state. We can see here the code also, and our Q values are updated based on current estimate, immediate reward, that is Q reduction, and best future value based on best future value also. This is the Bellman equation used here. So number 8 question is the yellow signal phase. Here we assign yellow signal phase after every green phase, and yellow phase is 1 and 3. So 0 is for main road green, and yellow is for phase after 0 action, and 3 is the another yellow phase which is assigned after side road green, that is 2. Here we can see that we provide 3-second yellow for after each green phase. So this is mandatory to safely switch from green to green, avoid abrupt conflict. We provide 3-second yellow here. And in the 9 number question, the question is we skip a signal phase through this, or does we include threshold value? We do not use any threshold value. That is straightforward, but we can skip the phase because the action is 0 or 2. So from 0 it can be 0 again 0 it can be, if the side road or the minor road have very little very small number of traffic. And threshold, we do not have any threshold, but we do not have any minimum queue to switch. We didn't use pressure threshold or waiting time constraint. We can include that in for future. And decision is purely Q value and epsilon greedy policy, and the epsilon value is 0.1 here. What do you have in state? Yeah, that's all about here. And we are using purely Q learning based signal facing here. That's it all about. Thank you so much for watching my presentation, and I can show you the simulation run again. This is the simulation run. You can see the simulation run over here. Thank you so much.